Okay, so in this video, we're going to talk about relative rates of growth. This is a really, really nice section. Hopefully, as you walk away, it's not only going to be incredibly intuitive, but it's going to save you a lot of time in what would otherwise be somewhat of a messy process. So to get things started, I want to just take a look at some very, very basic general functions. We've got the a to the x, which is acting like an exponential. We've got an x to the n, which is acting more or less like a polynomial. And then we've got our log base a of x, which is acting like a logarithm. And so when it comes to rates of growth, we're talking about which one grows faster. And so we're going to want to investigate these three types of functions as x goes to positive infinity. Okay? So what I want you to do actually is just to take a little bit of time. And pause the video and look at an example. Let's say y equals 3 to the x. Let's say y equals x cubed. And let's say y equals log base 3 of x. And I want you to go into Desmos and I want you to graph all three of these. Okay, once you see the graph, some things will be obvious when it comes to which one is growing more quickly as x goes to infinity. Certain things might not be as obvious. So from there, I think it would be a good idea for you to either on your calculator or on your computer then evaluate these at things like x equals 100, x equals 1,000, x equals 10,000, and take it up as far as you need to go until you can establish a definitive order for which function is growing faster than the others, and then put them in order as x goes to infinity. So again, pause the video, go ahead and play around with those three functions in Desmos, the numbers in your calculator or your computer, and then jump back in and we'll talk about how we can generalize this whole idea of rate of growth with these three particular functions. All right, so hopefully you were able to tell after playing around with that a little bit. And so we can generalize now. For rates of growth, we probably saw that log base a of x is less than x sub n is less than a to the x, of course, as x goes to positive infinity. So you found out that the exponential function was the fastest growing, the polynomial was the middle, and the log was the slowest growing. So let me generalize this even a little bit more. I'll say logs are less than polynomials, are less than exponentials in a general sense, and I'm actually going to tack on one more thing. The fastest growing, the most powerful function is actually a factorial. So if you want to take a few minutes and look at something like maybe x to the n in that same context, you would find out that that factorial is going to overpower all of the other three. But this is a really good piece of information to hang on to right here. And again, it's very informally stated, but it's going to be really, really helpful in the grand scheme. So let me show you what I mean by this. We'll take a look at our first example. The limit as x goes to positive infinity of x to the 15th over e to the x. Now, you could certainly do this limit using L'Hopital's rule. Okay, you could, and quite honestly, I'd do it 15 times, but you could do it. So instead of doing it 15 times, what I would recommend is that you just identify what function is the most powerful. Well, just a moment ago, we said the exponential is more powerful than the polynomial. So this guy right here is going to dominate the overall function. And as we go to infinity, what we're looking at now is the ratio of something small over something big. And at infinity, small over big goes off to 0. All right, that means the denominator is much bigger than the numerator, something like 5 over 10 million. Right? If you punch that in a calculator, that's going to be really, really close to 0, and we're not even nearly close to infinity. So small over big would go to 0, and so that's going to save you a lot of time then in understanding what this limit's going to do by understanding this simple boxed-in information here. Okay, so here's another example, and this is one where we actually are comparing a polynomial with itself. And if you had me for Calc 1, I've had this discussion with you before, but now it's a little more formally stated. So now, when we look at a limit at infinity, and again, you could use Calc 1 techniques on this. Honestly, you could use L'Hopital's rule on this as well, but I don't think we need to. We can see that from the problem, in the numerator, this guy right here is going to overpower the other two terms. Okay, so when it comes to infinity, this guy is going to be the dominant term of the numerator. Similar in the denominator. This guy is going to overpower these other two. So in the denominator, that's our powerful term. So when it comes to actually figuring out this limit, all I really care about is this 3x to the fourth over 9x squared. And so, yeah, they're still polynomials, but it's very, very clear that this polynomial right here, being as it's x to the fourth, is going to dominate the x squared. And so, again, the 3 and the 9, I don't really care about the 3 and the 9. That stuff I could even take outside the limit if I needed to. But it's the x to the fourth dominating the x squared. So when it comes to bigs and smalls, we have a big quantity over a small quantity. And as x goes to infinity, that would imply this thing blows up itself to positive infinity. Okay? So again, a much more efficient way of determining that limit without having to go through the mechanical processes that you learned in either Calc 1 or L'Hopital's rule. Okay, for this one, we're also, again, comparing against itself. We've got an exponential in the numerator. We've got an exponential in the denominator. Now, I'm going to be a little more careful here because we are going to negative infinity. It's not that this is going to change the overall question, but we just need to be careful to make sure we take that into consideration. And so what I might say is this. Since x is going to negative infinity, we might now consider a 3x over 2x as x now goes to positive infinity. Okay, this is going to now let me view the limit as x goes to positive infinity of 3 to the x over 2 to the x. By me changing it, notice I went ahead and I flipped it because of the negative exponent that would have been there, and then the double negative, of course, allows me to consider a positive infinity as well. Okay, so in doing that, again, we're comparing exponentials against itself, but that's okay. It's very, very clear, I feel, that this exponential would dominate the 2 to the x on bottom. And so here we're dealing with a big over small again, which would go off to that positive infinity. Okay, so again, rewriting this as this is really just a little bit of algebra. That negative that I would originally plugged in there would have caused these things to flip, and so had I done that, now we'd be dealing with that positive infinity instead. So just a little bit of algebra makes this one a lot easier as well, but either way, it still avoids us or allows us to avoid any messy computations, simply understanding this big over small. Okay, so for the final example now, we're back to going to positive infinity, and we've got a polynomial on top, and we've got a polynomial under a radical on the bottom. So let's focus on dominant terms. Clearly the x squared would dominate there. And in the denominator, this x to the fourth would dominate over these two other terms. So when it comes to the limit, all that we really care about now is the x squared on top and the square root of x to the fourth on bottom. But now, the square root of x to the fourth, as we approach positive infinity, right? So the x values are all positive that we care about, is going to simply give us an x squared over an x squared, which that limit goes off to 1. So it didn't necessarily blow up to one of the infinities or go to a 0 like we saw in some previous problems, understanding that the dominant part down here and being underneath the radical would allow us to simplify. It makes this limit very, very simple to compute without ever really even having that big over small conversation. So again, guys, I would encourage you to read the textbook as always, but this is some really, really good stuff. Not only will it save you some time in dealing with the limits, but later in the course when we talk about infinite series, we're going to have to talk a lot about these comparisons as well, and so it'll come into play in a few chapters. So good section. Take some time to really understand it.